Right now, there is a machine sitting in your bathroom that has not had a real upgrade in almost 250 years. Every single time you use it, it takes about 1.5 gallons of clean, treated drinking water and throws it straight down a hole. But in a lab outside Boston, a team of American engineers has built a toilet that uses no water at all, connects to no pipes, needs no sewer, and makes most of the waste quietly disappear into thin air. If this thing works at scale, the porcelain bowl in your house could become as outdated as the outhouse it replaced. This is not science fiction. It is a real piece of materials engineering that could change how we handle waste, how we use water, and how we build homes in places where plumbing has never existed. If you are enjoying videos like this, please hit the like button because it takes a lot of effort to make these, and subscribe so you do not miss the next one. The technology hiding inside this new machine is almost embarrassingly simple to understand. It is not a robot. It is not powered by artificial intelligence. It is a sheet of specially designed plastic. But it took engineers decades to figure out how to make that sheet of plastic behave the way they needed it to. The American team that finally cracked it did something nobody else in the sanitation world had seriously tried. They stopped trying to treat the waste and started trying to erase most of it entirely. What they built has no flush, no tank, no trap, and no drain. And to understand why that is such a big deal, you first need to understand exactly what is hiding inside the machine in your bathroom right now. Think about every toilet you have ever used. The one in your house, the one at your office, the one at the gas station on the highway, the one on the airplane, in the hospital, at the school. They almost all run on the same basic idea. And that idea is a lot older than most people realize. It is called the flush toilet. The critical piece of it, the part that made indoor bathrooms possible, at all was patented by a Scottish watchmaker named Alexander coming back in 1775. His invention was not the bowl itself. It was the bend. He put a curved pipe underneath the bowl and a shaped trap that stays permanently filled with water. That trapped water forms a seal. It blocks sewer gas from floating back up into your house. That one curve is the reason we were able to move the bathroom from a shack in the backyard into the middle of our homes. It is one of the most quietly important inventions in human history. Public health researchers have repeatedly ranked modern sanitation as one of the single biggest life-extending advances ever made, bigger than most individual medicines. Before it, cities were death traps. Cholera outbreaks wiped out entire neighborhoods because human waste and drinking water mixed in the streets. The flush toilet and the sewer system pulled us out of that. And yet almost nobody stops to think about how it actually works. Here is the whole thing in simple terms. You press a tank of clean water dumps into the bowl. Gravity and pressure push everything over that S-bend and into a pipe. That pipe joins a bigger pipe. That bigger pipe joins an even bigger pipe. Eventually, everything from your house and thousands of other houses arrives at a treatment plant where enormous amounts of energy and chemistry are used to separate the waste back out of the water we just mixed it into. Read that again, because it is the strangest part. We take clean, expensive, drinkable water. We deliberately contaminate it with waste. Then we spend a fortune cleaning it again. The numbers are genuinely uncomfortable. In the United States, the Environmental Protection Agency has estimated that toilets account for roughly 1/4 of all indoor household water used, more than showers, more than laundry, more than dishes. Older toilets built before efficiency standards can use 3.5 gallons or more per flush. A family of 4 can send tens of thousands of gallons of treated drinking water down the drain every single year. And not one drop of it was ever dirty when it went in. Then there is the infrastructure problem, which is worse. A flush toilet is not really a product. It is the visible tip of a buried machine that stretches for hundreds of miles. Pipes, pumps, lift stations, treatment plants. America has more than 1 million miles of that buried network, and enormous stretches of it were laid down generations ago. Civil engineering groups have spent years warning that this system is aging faster than we are repairing it, and that the bill to fix it runs into the hundreds of billions of dollars. And that is in a wealthy country where the system already exists. Step outside of that, and the picture changes completely. The World Health Organization and UNICEF have tracked this for decades, and their conclusion is blunt. Billions of people around the world still do not have access to safely managed sanitation. Hundreds of millions still have no toilet at all. For those people, the flush toilet is not an outdated technology. It is an impossible one, because you cannot install a flush toilet without water. And you cannot install a sewer without a city willing to spend a fortune digging under it. So, the flush toilet, for all its brilliance, has 3 hard limits. It needs clean water it does not deserve. It needs a buried network that costs a fortune. And it needs a treatment plant at the end of the line to undo the mess it just made. For most of the last century, engineers responded to that by trying to make the flush toilet slightly better low-flow models, dual flush buttons, pressure-assisted bowls. All of it was useful, and all of it was working within the same 200. Nobody was questioning the idea itself. Then about 15 years ago, a very large amount of money got thrown at a very simple question. What if we deleted the pipe? In 2011, the Gates Foundation launched something it called the Reinvent the Toilet Challenge. The rules were harsh on purpose. Build a toilet that needs no connection to a sewer, no connection to water, no connection to the electrical grid, and do it for a running cost of pennies per user per day. Universities all over the world took the money and got to work. What came back was fascinating and, for the most part, unusable in the real world. Some teams built toilets that burned waste at extremely high temperatures. Incineration works, but it eats energy and needs serious hardware. Some built machines that used electrochemistry to break waste down into fertilizer and hydrogen. Brilliant chemistry, expensive parts. Some built compact treatment systems that filtered and disinfected the water for reuse, essentially shrinking an entire municipal treatment plant into a box the size of a refrigerator. Every one of those approaches shared the same fundamental assumption. They all accepted that the waste had to be processed, heated, filtered, zapped, digested, disinfected, and processing takes energy. And energy means either a grid connection, a generator, or a solar array with batteries. And every one of those adds cost and adds something that can break. So the prototypes worked in the lab, and then they went into the field, and the field ate them alive. Filters clogged. Solar panels were stolen. Batteries died. Parts needed a trained technician who was 400 miles away. Report after report from pilot programs came back with the same theme. The science was sound and the maintenance was impossible. Meanwhile, a much smaller idea had been sitting in the corner of the room the entire time, and almost nobody was looking at it. Here is that idea. Human waste is mostly water. Not a little bit overwhelmingly, depending on how you measure it. Urine is roughly 95% water, and solid waste is around 3/4 water. When you empty a container of human waste, you are mostly moving water around. The actual dry solid material at the bottom of it is a tiny fraction of the total volume. So a very obvious question sits there waiting. What if you did not treat the waste at all? What if you just took the water out and let it leave as vapor and dealt only with the small amount that is left? That is not a chemistry problem. That is a plumbing problem solved with physics. And the physics has a name that has existed for a long time. Think about how sweat works. Your body does not cool you down by pumping refrigerant. It pushes water to the surface of your skin and the air takes it away. No moving parts, no power source, no fuel, just a surface, some water, and the air outside. Evaporation is one of the most efficient mass transfer processes in nature, and it has been running on this planet for free for billions of years. The problem is that you cannot just leave a bucket of waste open to the air and call it a toilet. If you did, 3 things would happen immediately. It would smell catastrophic. It would attract flies and become a disease vector, which is the exact opposite of what a toilet is for. And the water would not stay gone reliably. Evaporation is not selective on its own. You need something in between that lets water molecules escape while trapping absolutely everything else. You need a one-way door for water. Material scientists have chased that door for decades. It is a whole field called membrane science, and it powers things you already rely on without knowing it. Reverse osmosis, membranes, make drinking water out of seawater. Selective membranes separate gases in industrial plants. The waterproof but breathable fabric in a good rain jacket is a consumer version of the same principle. It stops liquid water from getting in while letting water vapor from your body get out. So, the theory was never the hard part. The hard part was that most membranes built for this kind of job are diabolical to keep working. Push dirty liquid against the membrane and the membrane fouls. A layer of gunk builds up on the surface. The pores clog and performance falls off a cliff. Then you need to backwash it, which needs a pump, or you need pressure to force liquid through, which needs a pump. And the second you add a pump, you have added the exact thing you were trying to escape: power. Moving parts, maintenance, failure. For a very long time, that was the wall. Everyone knew evaporation could shrink the problem by an enormous factor. Nobody could build a membrane that would do it in a filthy environment for years without electricity and without anyone touching it. Then a team in the United States took a different swing at it. And the thing they changed was not the membrane's filtering power. It was what the membrane wanted. Change. Waterless is a small American company founded by Diana Hughes, an engineer and scientist with a background that runs through both hard science and international development. The company came out of the Massachusetts innovation ecosystem, the same ecosystem that spins out dozens of MIT-adjacent hardware startups every year, and it has been backed and recognized by organizations working on global sanitation. Their product is called the iThrone, and the pitch is almost aggressive in its simplicity. It is a toilet with no water, no plumbing, no sewer, no grid power, and no moving parts. Instead of building a filter that liquid gets pushed through, they built a liner out of a hydrophilic polymer. Hydrophilic means water-loving. This is the crucial reversal. A normal filter is passive. It sits there and waits for pressure to push water through it. This material is not passive. It actively pulls water molecules into itself, moves them through the thickness of the material, and releases them from the outer surface as pure vapor. The material effectively sweats. And because the driving force is the material's own affinity for water plus the humidity difference with the air outside, it does not need a pump. It does not need a heater. It does not need electricity. Ambient air does the work the same way. A wet shirt on a clothesline does not need a machine to dry. Everything that is not a water molecule gets left behind. Pathogens, bacteria, solids, salts, odor compounds, they are all far too large or too chemically different to make the trip. They stay sealed inside the liner on the inside of the door. Only clean vapor gets out. The numbers the company reports are the part that make engineers sit up. Their system, they say, can eliminate the overwhelming majority of waste volume on the order of 90 to 95% or more purely through evaporation using no external power at all. A container that would have filled up in a couple of days now takes weeks or months. And because the water is being continuously removed rather than sitting and fermenting in a sealed anaerobic soup, the smell problem largely solves itself. Bad odor in a pit latrine is a byproduct of stagnant, wet decomposition. Take the water out fast enough, and you take out the conditions that produce it. Stop and think about what that actually means in practice. Every pit latrine, every portable toilet, every septic system in the world has to be emptied. That emptying is not free. A truck has to drive to it. A pump has to suck it out. And that truck has to drive somewhere else to dump it. That entire industry exists to transport water. If you can delete 95% of the volume before the truck ever arrives, you have not made the truck more efficient. You have made most of the trips unnecessary. This is what makes the approach different from every other reinvented toilet. The other teams built smaller treatment plants. This team built something that reduces how much there is to treat in the first place. It is the difference between building a faster boat and realizing you do not need to cross the river. And it is completely passive. There is no compressor humming. There is no fan. There is no battery to die in the cold. There is no filter to backwash, no electrode to replace, no burner to relax. It is a container and a smart piece of plastic quietly breathing. But the team quickly ran into something they had not fully planned for. Once you have built a passive, powerless machine that removes water from a dirty liquid using nothing but ambient air, you have not just built a toilet. You have built a general-purpose tool. And people started asking for it in places nobody had a bathroom in mind. The first and most obvious one is disaster relief. When a hurricane rips through a coastal town or an earthquake flattens a region, the water system and the sewer system fail together at the exact moment when tens of thousands of displaced people are packed into a small area. Sanitation collapse is one of the fastest ways a natural disaster turns into a disease outbreak. Historically, the answer has been rows of portable chemical toilets, which means a fleet of trucks on roads that may not exist anymore, hauling mostly water back and forth. A toilet that shrinks its own contents by an order of magnitude. and needs no hookup at all is a genuinely different logistical animal. Then there are refugee settlements and informal urban communities, which is the use case the technology was designed around in the first place. Some of these settlements have existed for years and hold populations the size of a mid-sized American city with no realistic path to a sewer network. You cannot trench and pipe a place that is not legally permanent, but you can hand it a toilet that needs nothing. Then it gets stranger. Construction sites. Anyone who has worked a job site knows the portable toilet and knows the servicing schedule that comes with it. National parks and trailheads where the current answer is a vault toilet that requires a pump truck to drive up a mountain. Long-haul trucking, RVs, and vans then. Enormous and growing. American market where the black tank is universally hated and dumping it is the single worst chore in the lifestyle. Tiny homes and off-grid cabins where the septic permit is frequently the most expensive and most restrictive part of the entire build. And then there's the one that sounds like a joke until you look at the engineering space. Water is the single most precious consumable on a spacecraft, and human waste is mostly water. Space agencies already run some of the most sophisticated water recovery systems ever built, reclaiming moisture from urine and even cabin humidity, because every liter you do not have to launch saves an enormous amount of money. A passive membrane that separates clean water vapor from waste with no pump and no power is exactly the kind of thing that gets a hard look from people designing long-duration missions where every watt and every moving part is a liability. The pattern here is the thing worth noticing. What started as a way to give sanitation to people without pipes is, underneath, a low-cost passive dewatering technology. And dewatering is a problem in food processing, in agriculture, in mining tailings, in industrial sludge handling. Anytime you are paying to move, store, or process something that is mostly water, the same trick applies. Take the water out where it sits, using the air that is already there. That is the exciting version of the story. Now, here is the honest version, because you deserve it. This is not sitting on a shelf at your local hardware store. And there is no announced date when a version of it is going to replace the bowl in your master bathroom. What exists today are working units and field pilots deployed in specific settings: Uganda, Panama, parts of the United States being tested and refined. Recent reports put the number of people who have used the system in the tens of thousands. That is a real and meaningful stage for a hardware company, and it is also very far from mass consumer availability. The hurdles that remain are serious, and they are not really scientific anymore. They are the boring, brutal kind. The first is throughput. Evaporation rate is governed by physics. You cannot argue with. It depends on the surface area of the membrane, the temperature, and crucially, the humidity and airflow of the environment around it. A unit that performs beautifully in dry, warm, moving air will slow down in cold, still, saturated air. Anyone who has tried to dry laundry outside in a humid climate already understands this intuitively. That means performance is not a single number. It is a range. And designing for the worst case rather than the brochure case is where a lot of promising hardware quietly dies. The second is scale and manufacturing cost. Specialty polymer membranes are not commodity plastic. Making them consistently in volume at a price that works for the exact markets that need them most is its own engineering discipline. And there is a cruel irony baked into this entire field, which is that the places with the most urgent need for it are the places least able to pay a premium for it. Sanitation technology has a long history of excellent products that were priced for a market that could not buy them. The third is durability and abuse. A toilet in a shared public setting takes a beating that a lab bench cannot simulate. It gets things thrown into it that are not waste. It gets cleaned with harsh chemicals that may attack the membrane. It sits in the sun. It gets kicked. Any single one of those can shorten the life of a material that is supposed to last for years without service. And the fourth is the one nobody in engineering likes to talk about, which is regulation and habit. Plumbing codes in developed countries are written around the assumption of a sewer or septic connection. Getting a fundamentally different device approved for residential use in the United States is a year jurisdiction by jurisdiction grind. And beyond the code there is the simple human fact that people have very strong feelings about their toilets, and it does not flush, is a sentence that makes most homeowners deeply uncomfortable no matter how good the physics is. So the wall between this technology and your bathroom has not vanished. It has moved. What the American team solved was the technical bottleneck that made passive, powerless waste reduction impractical for decades. What remains is manufacturing cost, durability, and the slow, grinding process of convincing the world to change something it has not thought about since 1775. But this is exactly how every major technology begins. The first computers filled entire rooms and cost more than a house. The first solar panels were so expensive they were essentially only viable on satellites. The first electric cars were golf carts with delusions of grandeur. In every case, the invention arrived in a strange form in an unglamorous niche, solving a problem most people did not think they had. And then it got cheaper, and it got better, and one day, it was simply everywhere. There is something genuinely odd about sitting with this. The single most used machine in your home runs on an idea a watchmaker sketched out before the United States existed. We have redesigned the car, the phone, the television, the light bulb, and the map, some of them 3 or 4 times over. The toilet got a smaller tank. And now, a small group of American engineers is quietly suggesting that the entire premise was backwards. That the goal was never to build a better way to move waste. That the goal was to stop moving it at all. Not with something loud or flashy, but with a sheet of plastic that sweats doing in silence what 1,000,000 miles of buried pipe currently does at enormous expense. Technology like this rarely arrives all at once. It arrives in small, unglamorous steps in field pilots most people will never hear about, years before it ever shows up in a store. But one day, the flushing sound that has been part of human life for 2.5 centuries might just stop, replaced by absolutely nothing at all. If you enjoyed this story and want to see more like it, hit the like button, subscribe, and turn on notifications so you never miss the next one. There are related videos on the screen right now if you want to keep watching. So here is a question for you. Which everyday machine in your home do you think has gone the longest without a real upgrade? Let me know in the comments!